I'm Evan Kuester. I'm an advanced applications engineer for 3D Systems, and I'm currently located in San Francisco and work for the Advanced Applications Department, which is headed up by Patrick Dunn. Some of you may have known him or may have heard his name before. And what we do at this department is basically sort of explore I guess, what are the sort of novel aspects you can use for 3D printing, or some of the problems you can solve that only 3D printing can solve, or I guess, how do you design things that aren't, I guess, traditionally manufacturable? And so since 3D printing allows basically for free complexity, you can design parts that are obviously you could never make before, or it would cost way too much money to make before. Like, for example, this turbocharger, which we printed with, or this one's not been printed yet, but we would like to cast it. But it's a real, basically the wall sections on this turbocharger are 1 millimeter thick, if not thinner than that. And then we've reinforced it with an external structure. And so I'm going to basically teach you guys how we did that, or sort of the logic behind it, and that kind of techniques involved with creating some of these objects. And so I guess, unless anyone has any questions to start off with, let's begin. Oh, also, because this event is being recorded, could you please silence your phones so we don't get any like phone ringing during this presentation? All right. So these are some examples of traditionally machined and traditionally produced metal parts, or these could be plastic parts or any kind of parts, but very bulky. They're like really simple CAD models in my personal opinion. They've got, I mean, there's way too much material on them, but I mean, I guess this is how we used to traditionally manufacture things. I personally have actually really only learned how to design for 3D printing, and so some of these, like, the limitations that CNC applies is so limiting to me that it's kind of hard for me to understand why anyone would CNC certain objects when you could print them much better and much lighter and faster and stronger and have a lot more design iterations in it in a much shorter period of time. And so, I mean, say for instance, just like it's really hard to, I'm assuming, to CNC one of these impellers. Like, that's a challenging part to make, where in 3D printing with any metal printer, that's actually pretty easy to make. And so, and you can go way beyond just this sort of simple shape here. You can add kind of textures onto the surface that improve airflow across the surface of the impeller. Like, you can push it way beyond anything you could ever make with a traditional CNC or injection molding or anything else like that. And so, for instance, this for instance is 3 separate parts with 4 screws that come together to create this bracket. If you were to print this in metal, this would be 1 part with 2 screws in it. And so it's not only easier to design, there's less parts and less points of failure, and it's just an overall better part if you were to print it. And so this is an example of basically a traditional manufactured part, like standard CNCing. And then these are some examples of some parts that have been optimized for 3D printing. And so since complexity is free, you can basically explore as you want and then design parts that meet your specific needs rather than the needs of the machines. Then you're sort of kind of surrendering some of the design process and some of the design thinking to the limitations of the techniques you're used to make it. And so, for example, we do a lot of medical devices at 3D Systems, and 3D printing is a fantastic pair with medicine, since all the devices are basically custom, and 3D printing is really good at making custom devices. And so this is, I think, a drill guide for a tibia and a fibia. And I mean, there's other hearing aids, ball and socket joints, surgical planning devices, all these things that traditionally you wouldn't really ever make, or if you made them, they were kind of one-offs, and if they were one-offs, they were really expensive to make. And so not the easiest things to make with sort of injection molding. And so, and this is also, like, you can even injection mold tools. I mean, you can injection mold tools. You can 3D print injection molding tools. And so this is an example of sort of the first couple of iterations of injection molding tools, and still these are really blocky parts to me. I guess this looks like a traditional injection molding tool, like a really thick, solid piece of steel. In this case, it's probably a high temperature plastic, but you can even refine the injection molding tool to reduce the weight by like 99%. On this part, for instance, it doesn't need to be a solid block of plastic. It could be hollow and full of a lattice, and we will go through that in a little bit. The first example I'm going to talk about is a company called And so what they are is actually, there's a video.
The promise of 3D printing lies in the creation of truly personalized products. Nowhere is this potential greater than in the treatment of respiratory disorders such as sleep apnea, where poor fit means poor function. Our platform unites 3D scanning, 3D printing, and smart geometry to create Respire, the world's first fully customized 3D printed CPAP mask. At MetaMason, we believe the future should not simply come in small, medium, and large. We think the only size that matters is the one that fits you perfectly.
So, their product is basically a silicone mask that goes over your face. They're all very similar, but custom to the individual, and so you can't make an injection molding tool for every single individual, or at least traditionally you couldn't make an injection molding tool for every individual who would buy this product. And so their challenge was basically, how do you make a custom molding tool that's cheap and fast to produce and produces a silicone part at the end? And so they had originally come to us with the part on the left there, the original file, which was, and they had been printing that mold in wax, and it was very heavy, and their business model hadn't been working because it was too expensive to print these molds in wax. And so, but that's what they had been, printing them in wax, filling them full of silicone, and then melting the wax off to get the silicone part out. And there had been other issues with the wax possibly contaminating the silicone, or just large series of issues that are related to basically using the wrong type of printer to do a job. And so not all printers are created equal. You can totally do something that's very difficult in one printer that's very easy on another. And so knowing when and where to use the right printer and technology is very important. And so what we did with this file is, after kind of thinking about how to basically make a molding tool that you could get off of a silicone part, why do you have to melt it off the part? In this case, if you printed it in wax, it was melting it off the part. And there's complex internal structures in here that are hard to like basically pull plastic out of. And so what we did is we basically created an eggshell, where we, instead of where a traditional casting process, you would thicken the inside of it, or you would basically hollow out the inside of a part, stick it in basically a bath of ceramic powder, or like a slip, pull it out, and then the ceramics would harden on the outside. You'd melt the part out of the middle, and then fill that full of whatever your material is. Maybe it's a metal or a plastic, or like traditional lost wax casting. And we basically reversed the system, and we printed basically an eggshell, where we took the geometry of the original file and thickened it to the exterior by about 0.5 millimeter. And so this created a shell around the outside of the part that we were then able to basically break off the part when we were done with filling it full of silicone. And so not only did it reduce the overall weight of the part, the original file weighed, I think, 87 grams. And then once we created the eggshell for the same mold, the new mold weighed 7 grams. And so the material usage went way down on producing these parts. And then for these eggshell, like the eggshell is actually quite novel in that when you're printing with an eggshell and filling it full of silicone, you can crush the part by literally, I've stepped on parts before, and then it basically just destroys the eggshell mold, and then you just peel it off like an eggshell, like a hard-boiled egg, and then you get your silicone part out of it. And so that was one of our sort of novel ways of molding very complex structures. I don't have an example of a lattice structure, but we've done lattice structures, nose pieces, fake ears, or prosthetic ears, prosthetic noses, basically anything you want in actual silicone, since printing in silicone is currently not that widespread. It's way easier just to inject something full of silicone and move on. And so this is an example of the mold and the final part. The mold on the left was printed on a SLA printer in Joule, or in our case it was one of our materials, Joule, but any SLA printer should work. And it's basically an eggshell of that part that's 0.5 millimeter thick. And it prints in some cases, an hour or two. And so that's a really quick way of creating a custom injection molding piece. And I'm going to show you very quickly how we made that. And so MetaMason was nice enough to let us use their part as an example. And so let me open these parts and magics. So basically just going to import their original mold file. And parts, MetaMason. And so this was their original file. And as we can see with some part information over on this side, the volume of this part, like the internal space, the material used would be 52,756 cubic millimeters of whatever the material it is you're making. And so originally this was like, how do we create, and we didn't even ever have the original CAD file. I'd never had the standard step file or whatever I think they generated it in Rhino with Grasshopper, but I've never even got to see that part. I was only ever allowed, or not allowed, to work with this mold. And so right away, there's a lot of material here. Like if I take a cross section of this, basically the gray space is where the silicone will go, and all the red is just material for the mold. And that's a lot of material that you don't need, and you're basically wasting because you're going to melt it out and throw it away. And so the less stuff you can throw away at the end of the day, the better it is for both you and the planet, and saving money and all of those nice things. And so this was really just as simple as selecting the external shell, deleting it off. And so now we've got basically an inversed version of their final product. And so I'm just going to go around very quickly and click on some other little details that I need to get rid of before the next step. Delete. And that one, actually no, I'm not going to delete that one. And then literally surface to solid 0.3. In this case, we were using a 0.3 millimeter shell, 0.3 millimeters for the detail, and then it'll take a second, of course, to basically make this back into a solid from a two-dimensional surface, or a two-dimensional mesh in this case. And so, poop, now there we go. We have a nice eggshell mold of that part in a very short period of time. And so, and it also did the sprues and the vents on it as well. And so a lot of times I'll just design a part, like just the final product, like this mouse, for instance, put the sprues and the vents and the drains and anything you need to do for injection molding or molding in general, or casting or whatever you would like to do. And then I just thicken it, which is very easy to do, particularly when it's a mesh, but you can do it as a surface file as well. But if we go back in here and take a cross section of this part, that overall red space is now very tiny. I'm wasting a very small amount of material now. And if we look at the part info, it went from 57,000 millimeters to 5,800 millimeters, cubic millimeters of material. And so that is, without doing any math, a pretty significant reduction in overall part volume. And so very, very easy, very quick way of doing this, and this file is basically ready to send to the printer and print. And so if your workflow was to basically create an injection molding mask or an injection molded part, you could, or a custom injection molding part, you could just add one more step into that sort of automated system, which would be just thicken, or thicken to the outside of the part so you don't destroy the internal geometries. If I was to do this in inverse, like go back to this point and then flip all the normals on this part, and then thicken to the inside of the part, I would destroy the geometry on the inside. So it is important the direction that you basically offset this part with. So that was one of my favorite examples for sort of how you can really quickly design a part to take advantage of a material or take advantage of a printing process that maybe wasn't working in another one. Like this in wax didn't work. This was way too heavy in wax.